Okay, differentiability is what we're going to talk about today. Differentiability. Write that word down. Probably one of the longest math words that we've done in this class. Okay? Can anybody take a stab at what they think that means? Different? That's pretty good. Okay. What do you think?
The ability for a point to be derived.
You're very, very close. Can almost say the ability for a point to be derived. Okay. Do you see that it's the ability to do something? Because it says ability at the end. Differentiability. The exact definition is the ability to be differentiated. We haven't really talked about the word differentiation in here, but we are going to talk about it today. First semester calculus in college is called differential calculus because differential and differentiable both mean the same thing as, what have we been talking about for the last week? Derivatives. So, differentiability means literally the ability to be differentiated or the ability to take the derivative of something. Now, everything we've done since we started derivatives, I've just said, here's a function, here's an equation, take the derivative. And you said, yes, Miss Bell, I will do that. And you just do it. Because I've given you, every time I've given you something that works. Now we're going to be looking at problems that might work and might not work and talk about whether or not they can be differentiated or can have the derivative taken. So on the board it says we will learn how to determine whether or not it can be differentiated or if it's differentiable, and then force certain functions to be differentiable by finding unknown values. Okay? So we're going to look at this from both a graphic and an algebraic perspective. What it means to be differentiable. So the first thing we're going to do is write down the definition, what we just said, and that is the ability to take a derivative. All right, we're going to kind of do a little review and talk about why we learn things in the order that we learn them. Excuse me. All right, what did we start this year learning about? Limits. Okay, let me ask you a question. You just finished a test yesterday. If I gave you a graph and put it under the camera, and it was a picture of a function, could you look at that graph and tell me whether or not the graph had a limit at a certain point? With confidence, do you feel like you could do that? Yes. Okay. In order for a graph to have a limit, what do you have to see? The left-hand limit has to equal the right-hand limit. So let's write that down. The first thing we did was limits. And a limit exists at x equals a if the left-hand limit equals the right-hand limit. Or if you wrote it in mathematical terms, the limit as x approaches a from the left of the function equals, I don't know why I put a parentheses around it, right there, not supposed to. The limit as x approaches a from the right of the function. That's what I meant to do. And you knew that. So I think that now that we've 4 weeks into the school year, 5 weeks into the school year, you guys feel pretty good about limits. You can look at a picture and say, yes, there is a limit here. No, there's not a limit there. Okay. The second thing we went on to after limits was what? Continuity. Very good. So if I put a picture under the screen and said, could you tell me if this graph is continuous at this point? Do you think you could do that? Of a function? Yes. Okay. So it is continuous at x equals a. What 3 things have to be equal? Left-hand limit has to equal right-hand limit has to equal what? F of a in this case, because I changed letters. F of a. Okay. So, do you see that that's just like a step above limits? Now we're going to go a step above continuity today with differentiability. So third and final step is differentiability. First thing I'm going to do is write down the definition of this in its formal form. And then we're going to look at an example from both a graphic and an algebraic perspective to see if we really understand what this is saying. So f of x is differentiable. And remember that means has a derivative at x equals a if the following two conditions are met. This one has two. Condition number one. F of x is continuous at x equals a. It must be continuous first. And number two is this. The limit as x approaches a from the left of the derivative of f is equal to the limit as x approaches a from the right of the derivative of f. So, by the end of class, you should be able to look at a graph and tell me if it's differentiable. Now, you can tell by looking at a graph if it's what does this look like? What does it look like? You may not know because that's all limit jargon. What it's saying is that the limit of the derivative from the left is the limit of the derivative from the right, or you will slope as you approach x equals a from both sides. You will see the same slope as you approach x equals a from both sides. Now, you may think, that's not really easy. I can't always look at a graph and know what its slope is. Well, there are going to be some obvious looking things that are going to make it a little bit easier for you, okay? When I give you a picture of a graph and I ask you what the y value is, that's pretty easy to look at and figure out. But when I ask you to see a graph and see what its slope is, that's not as easy. So what we're going to do is through these examples, we're going to look at some pictures and you're going to be able to know, oh, if I see this thing on a graph, that means it's not differentiable. Or, oh, if I see that thing, it's not differentiable. Okay? So let's take our first example. And it's going to be a very simple parent function that you have seen before. And that parent function is absolute value. The question for this problem, is it differentiable? DIFF is the accepted abbreviation for differentiable at x equals 0. So, since we're going to look at this from a graphic perspective also, let's go ahead and graph this thing. Do you remember what absolute value looks like? It's a V with its vertex where? At the origin. So, please draw that in. Is that thing differentiable at 0? Well, I don't know yet. We're going to figure it out. We're going to use both the graph and the algebra to prove one way or the other whether it is. Okay? Now, I have not given you a absolute value problem to take the derivative of yet because you cannot take the derivative of an absolute value in this form. It can't be done. What you have to do first is to break it into the piecewise function that it actually is. And I don't know if anybody's ever shown you this, but absolute value is basically a piecewise function. Okay, let's look at the right-hand piece first. What is the equation of that line right there? Y equals x, right? Because it's got a slope of 1, goes through the origin. So this is x as long as x is greater than 0. Agreed? What about the other side? That's negative x. Very good. As long as x is less than 0. Now, here's the question. Do you notice that I did not put a equal to on either one of those? which one should get it? Talk to each other. Talk to each other. Which one should get it? Which one should get the equal to sign? Okay. So, the choices are equation 1, equation 2, both, or neither. Or it doesn't matter. There's actually a fifth choice. Okay, equation 1, equation 2, both, neither, or it doesn't matter. Okay. Is anybody gung-ho that it has to be one or the other? Okay. How many of you think it might be both? Raise your hand. And that's a valid answer. That is a valid answer. Okay. Now, I want to show you that it would work in both. The only problem is there's a slight flaw to it. Okay. This is equation 1 over here, right? This is equation 2 over here. When you're defining it at 0, you cannot define it at two different equations. I can't say 1 and 2 right there. I have to pick one. And if it, does anybody think it might be neither? Okay. Neither would imply that there was a hole in the graph at 0. Is there a hole in the graph of absolute value? No. So there, we have to pick one. We have to pick one. Okay? Now, the key is we have to pick one. We cannot pick both. And since we have to pick one and both work, it doesn't matter which one you pick. You get the freedom to pick whichever one you want. Did anybody think that was the case? Raise your hand if you thought that was the case. A couple people up here did. So, right now, pick your favorite function. Put it on whichever one you want. I don't care. I'm going to put on the first one. Okay. Has to be one of them. So that means that equation 1 is the one defined at 0 for my graph. All right. Okay. Since, let's go back to what we're doing. Yeah, I got off on a tangent there, but it's kind of a good tangent. We're trying to find out if it's differentiable. Well, continuity we'll talk about in a minute, but I need to know something about the derivative. So what I'm going to have to do is take the derivative of this piecewise function. Now, we've not done this before. Or maybe, I don't think this was on that worksheet. When you take the derivative of a piecewise function, you take the derivative of each piece. It's not very hard. So, look at equation 1. What's the derivative of an x? 1. So write down a 1, comma, x is greater than but not equal to 0, and I'll tell you why in a minute. Equation 2, what's its derivative? -1. We're using the shortcuts, remember? X is less than 0. Now, put a little arrow pointing to that first one and write the following. Do not put equal to 0 because we don't know if it is differentiable yet. Okay. Write that down and then I'll explain what I mean. I'm going to write this in a minute. Is this graph up here continuous? Is this graph, is absolute value continuous? Yes. Because it's continuous, I know there's a y value at 0. And I knew it could be either one of those because it's continuous. Okay? I don't know yet whether or not this thing is differentiable. So I cannot say which one of these gets the equal to sign. Because I don't know yet. I have to do the math first, then come back and do it if it is differentiable. Okay? So, here's what we're going to do. We've got to answer the two questions that were listed right here. F of x is continuous at x equals 0? Yes or no? Yes, we just said that. Yes. So, yes, it's continuous. And let me reiterate this. If step 1 fails, if it's not continuous, game over. You don't even bother going on to step 2 because it's automatically not differentiable. Okay? Since I got a yes, I got to keep going. So now write this sentence down. You're going to write limit as x approaches a from the left of the derivative equal to and put a question mark on top of it. And that means we're going to test it and see, does the limit from the left equal the limit as x approaches a from the right of the derivative? Does the limit from the left equal the limit from the right? That's how you read that as a math sentence. I don't know. Well, I'm about to find out. Okay. When you take the limit of a derivative, you take the limit just like you would a function. You go plug that number in, okay? Which equation is the left-hand limit equation? First or second? Second. So what is the limit as x approaches 0? Negative 1. Write it down. Equals 2 with a question mark on top. That means the other equation is the limit from the right. What does it equal? Positive 1. Are those two things equal to each other? No. Negative 1 does not equal positive 1. Therefore, f is not differentiable at x equals 0. And if you go back to what we wrote in red, that means that neither one gets the equal sign because it's not differentiable. Okay? Neither one gets the equal sign. All right. So let's talk about this from both an algebraic and a graphic perspective, because now we actually have a picture of our first non-differentiable point. Does the math here make sense to you? We had the function, we took its derivative, and then we checked the left and right hand limit of the derivative. They came out different, not differentiable. Pretty straightforward. Look at that picture. Let's talk about it picture-wise, because some of your brains work better with graphics than they do with algebra, okay? Now I'm going to move these aside because I'm going to put it under the camera. What's the slope of this side of the graph? 1. What's the slope of this side of the graph? Negative 1. As you get closer and closer to the origin, are those slopes going to change at all? No. So when the slopes hit this point, it's kind of like the point can't choose which slope to take. It's got 1 coming in from this side. It's got negative 1 coming in from this side. Can't make up its mind. Therefore, it's not differentiable. Does that make sense? So, this right here is called a sharp corner. And it's true of any two lines as long as they're straight. If two straight lines meet at a point, you're never going to have a derivative there, because the slope of one line is going to be different from the slope of the other line. Does that make sense to y'all? Okay, so keep that in the back of your mind. Sharp corners are one picture that don't have derivatives. All right, let's go on to picture number 2. I'm not going to show you the picture of this one till the very end. This is what the homework is going to look like.
Isabel,
Yes?
is that last graph a cusp or no?
No, and we're going to talk about cusp in just a minute. Okay, a cusp and a sharp corner are two different things. And we'll talk about that in a minute. Determine if f is continuous or discontinuous. Okay, I forgot to do this earlier. I'm going to do it now as you're writing. Just think for a minute. Think your brain can engage while your hand is writing. Do you remember the 3 types of discontinuity? And infinite. Jump, point, and could you recognize all 3 on a graph? Yes. Okay. I'm going to teach you today the 3 types of non-differentiable points so that you can recognize them on a graph as well. Okay? So part A, determine if the function is continuous. Part B, determine if f is differentiable or not differentiable. I'm not writing very well today. Non-differentiable. We don't say dis-differentiable. That sounds kind of funny. Okay, here's our function. And it is a piecewise. 2x minus 3. X is greater than or equal to 2. Negative x squared plus 5. X is less than 2. Okay. 2x minus 3, x is greater than or equal to 2. Negative x squared plus 5, x is less than 2. All right. Now, the last problem said, is this not differentiable at 0? This one doesn't tell me a point. So how do I know where to look? Well, let's take a look at this. First equation. What kind of graph is that? Linear. Are linears continuous? They have to be continuous. That's what we're looking for, is continuity. What's the second graph? Parabola. Is it continuous everywhere? Yes. So the only possible point of discontinuity is the point where the two graphs potentially meet, where one graph starts and the other one stops, right? So the point in question here is x equals 2. So what I'm going to do is I'm going to go ahead and draw the number line. If you need it, draw it. If not, you can just watch me. So greater than 2, that's the right side. Less than 2 is the left side. Which one is equal to 2? 1. Okay. So, part A says determine if f is continuous or discontinuous. I believe on the test you took over the last 2 days that you had to do this. Yes? Okay. So, tell me again the 3 things that have to be true for a function to be continuous. Left-hand limit, right-hand limit, f of a. Okay. Do you understand why I'm making you remember this all the time? You need to know it all year long. And the more you say it now, the more you'll remember it in March. So let's write this down. Limit as x approaches 2 from the left of the function equals. Scoot over some. The limit as x approaches 2 from the right of the function. And then f of 2. Those are the 3 things that have to be equal. Okay. Since you just did this on a test, I'm going to give you about 45 seconds to work with your table and do this right now. Tell me what the left-hand limit, the right-hand limit, and f of 2 are. You may talk to each other. Okay, time's up. All right. Let me see. Who do I want to talk to today? Who's my victim today? Logan. Left-hand limit. What do you think? 1. Which equation did you plug it into? The second one. Okay. So we have negative 2 squared plus 5. Now, does that definitely equal 1? Yes, because squaring, which is exponents, comes before multiplying, which is the negative. Okay. We had a big discussion about this second period. Negative 2 squared plus 5 is 1. So that answers 1. Okay. Let me think. Faria, what's 2 from the right? Positive 1, so 2 times 2 minus 3, positive 1. F of 2, which in the first equation, we've already done the math, so we don't need to show the math. Is this function continuous at 1? So right, therefore, 3 dots, f of x is continuous at x equals 1, x equals 2. Not 1, x equals 2. Okay, we all good on that? Okay, so we did part A. Now we need to do part B. Let me say this one more time. If this had come out to be not continuous, you don't even have to do part B. Because if it's not continuous, it can't be differentiable. Does that make sense? Part B. First thing we must do is take the derivative of this function, because we're going to be setting their limits equal to each other. So, come back up here, point to the original equation. What is the derivative of equation 1? 2. And then move over. X is greater than, but not equal to 2. Remember? And then the derivative of the other one. Negative 2. Negative 2? X. Oh, thank you. X is less than 2. Y'all agree with that? Okay. Now, to test if it's differentiable at 2, we got to take the limit as x approaches 2 from the left of the derivative, and then the limit as x approaches 2 from the right of the derivative. Okay, so we don't even need the original function anymore. We're just looking at the derivative. Which equation are we plugging into for the left-hand limit of the derivative? 1 or 2? 2. So this would be negative 2 times 2, which is negative 4. Okay. And then the limit from the right is the first equation, so that's just 2, because there's nothing to plug in. Is this function differentiable at 2? No. Therefore, f is not differentiable, and you can abbreviate, at x equals 2. All right. Now, this is definitely not a sharp corner right here. Even though it's not differentiable, it's definitely not a sharp corner because I've got a line connecting to a parabola. So let's take a look at what it does look like. And I have this already plugged into my graph. Just give me a minute. So move over there, turn that on, move over there, turn that on, turn that off. And let's graph this thing on Zoom 6. Okay, give it a second to come in. There is that graph. And I can't zoom it in because I'm recording. Trying to get that up there so you can see it. What do you see, guys? I see a cusp. Okay. Cusps occur when a line or a curve connects to either another curve or a line. This is a curve connecting to a line. That's what makes a cusp.
And if it's two lines, then it's a sharp.
And if it's two lines, it's a sharp corner. Exactly. Are you cool with that? Okay. So the two things we've talked about so far that you see, cusp and sharp corner. Okay. I'm going to show you the third. We're not going to do a problem associated with it, but come down here and write this down, please. The three types of non-differentiable points. So just like the three types of discontinuity, you know what they look like. Now you're going to know what the three types of non-differentiable points look like. We'll start with the one we just did, a cusp. That is a straight line connecting to a curve. That's a cusp. Or it's a curve connecting to a curve. That's a cusp also.
Or curve to curve.
Curve to curve is the other one, yeah. One must be curved. In order to be a cusp, one of them must be curved. Number two, sharp corner. And sharp corner is just what it sounds like it is. Two lines connecting. So both are lines when you're dealing with sharp corners.
So can you drop it that big?
No. Okay. The third one, I'm not going to do a problem with, but I'm just going to tell you what it is. It's called a vertical tangent. And I'm going to show you a graph of one of those on my calculator here. See if that can come up. Does anybody know what parent function that is?
Yeah.
E cubed.
Oh, okay, you're closer than you realize. Okay, it has something to do with a cubic. It's the cube root graph. It is the cube root graph. If it only graphed the right-hand side, it'd be a square root graph, pretty much. The steepness is slightly different. Okay, look at 0. Do you see what it's doing at 0? It's kind of doing this almost straight up and down before it turns. If I zoom in, it looks even better. Okay? Do you see how it almost goes straight up and down at 0? That's a vertical tangent. So what I want you to do is right here, I want you to draw something like that and draw in a dotted vertical line, because at that one point, it just almost goes straight up and down for a split second. And what will happen is that when you do the math, you will have limit as x approaching a of the derivative. And when you do it mathematically, you will end up getting an answer of infinity. Okay, now let's talk about why is it infinity. Derivative means the same thing as what? Slope. And when something is approaching infinity, what's it doing? It's going straight up. And that's what that slope is doing. It's a straight up and down slope. You follow what I'm saying? Okay. So that's the three different types to look at when you're looking at a picture. Either a cusp, a sharp corner, or a vertical tangent. So now you can look at a graph and say, ooh, it's not differentiable there. Ooh, it's not differentiable there. Okay? But also remember, it's not differentiable if it's not continuous to start with. Okay? So let's move on to the last question, which is taking care of the last part of the we will statement. We're going to find unknown values to force something to be differentiable. So, we're good on time. For example, find, can you see? Yes. the values of a and b that make the function differentiable. Find the values of a and b that make the function differentiable. And here is the function. F of x equals 3 minus x, where x is less than 1, and ax squared plus bx, where x is greater than or equal to 1. Three minus x for x is less than 1, ax squared plus bx for x is greater than or equal to 1. Okay. So, I'm going to say this one more time. I'm actually going to give it to you in the form of a fill-in-the-blank question. Fill in the blank. In order for a function to be differentiable, it must first be blank. The answer is continuous. So the first thing we're going to do is we are going to check the continuity. And you must do this every time. If it's not continuous, it can't be differentiable. So do what we did on the previous problem. We're going to do the limit as x approaches 1 from the left of the function. The limit as x approaches 1 from the right of the function. And f of 1. Okay. I'm going to stop talking for a minute, and I'm going to give you another 45 seconds to a minute to do this one, because I know you know how to do continuity. One or more of your answers may have A's and B's in it. That's okay. So try this real quick. See what you get. Let me talk to Iñaki. What's the left-hand limit? What'd you get?
I got 2.
You got 2. So, using the first equation, 3 minus 1 is 2. That's correct. Right-hand limit. Christina, go. A plus B. Do the rest of you get A plus B?
Yes.
Yes. A times 1 squared plus B times 1. Remember, you're supposed to show the work to show how you got it. Except for, unless you've already done it, then you don't have to do it again. What is F of 1? What do y'all think? A plus B again. Now, in order to be continuous, what has to be true about these three answers? Have to be equal. So, can you write a math sentence showing that? What would the math sentence say? A plus B has got to equal what? 2. There's your first math sentence. Okay. So, do you know with absolute certainty what A and B would be just from that? No. Could be lots of different things, couldn't it? Okay, so that means I don't have enough information to finish the problem, because the problem's asking me to find what A and B are. I don't know yet. But I do know they have to add up to be 2. All right, step 2. We need to check the differentiability, because that's what we're really looking for. I can't spell. Here we go. All right. In order to do differentiability, we got to take the derivative. And then we do the left-hand, right-hand limit of the derivative. So f prime of x equals. I have to pick up the pace a little bit to make sure I get done. What is the derivative of the first equation? -1. X is less than 1. Remember, don't put equals on any of these. Ooh. 2. Derivative of 2. It is 2ax. Does everybody see how we got that? Because a and b are constants. They just sit there. Plus what? B. Right. Bless you. X is greater than 1. Okay. So once you get your derivative, now we do the limit from the left and right. So limit x approaches 1 from the left of the derivative. Limit x approaches 1 from the right of the derivative. Okay. Which equation is the left-hand limit of the derivative? Equation 1. It's the same for both problems. So what is my limit? Negative 1, nothing to plug in, so you just copy it down. All right, carefully. What are we plugging 1 in for again? X. So this is going to be 2a times 1 plus b, which is 2a plus b. Okay? So in order to be differentiable, what do these two things have to be? Equal to each other. So our next math sentence says 2a plus b equals negative 1. Now, with just that information, do I know what a and b are? No. But if I use these in synchronization, I can find what they are. Do you remember doing something like that in Algebra 1? Do you remember what it's called? It's a system of equations, exactly. And what is the method called to solve it? There's a couple of them. Substitution, and what's the other one? Elimination. Okay? So, step 3, solve the system. So, copy the two equations down. A plus b equals 2. 2a plus b equals negative 1. Okay, well, let's do elimination. We need some practice with that. What letter should I eliminate? B. Which equation? What should I do? Change the signs of which equation you want to do. Most people like to do the bottom all the time. Top is actually easier, and if you know how to do the top, do the top. So, be careful when you do, though. That means that this is negative, and the 1 is positive. So when you combine the terms here for the a's, it's negative 1a. Those cross out, and you get positive 3 on the right. So a equals negative 3. I just found a. I'll move this up because I don't even need that above stuff anymore. To find b, go back to either equation and plug it in. Negative 3 plus b equals 2. So b equals, what do you say, guys? 5. Okay. Have I solved the problem that the question originally asked? Yes. Go back to the top and look. It said, find the values of a and b. Did I find the values of a and b? Yes, I did. Okay. That's a real big thing in calculus because sometimes the problems are so long, you forgot where you were going. You're like, wait, did I finish yet or not? Okay. I want to show you real quickly how to check these. And it's so fast and easy. Okay? What you need to do is take both the derivative and the original and plug in the values for a and b. Just write the equations down. So, watch this. F of x equals. So 3 minus x, x is less than 1. Negative 3x squared plus 5x, x is greater than or equal to 1. The derivative is negative 1 for x is less than 1. 2ax, 2 times negative 3 is negative 6x plus 5 for x is greater than 1. And now that we are forcing them to be differentiable, you can put the equals to on either one of these. I'm going to put it on that one. Okay, I'm going to box this in as the check. When you're checking, all you got to do is plug 1 into both pieces. If you get the same answer, you're good to go. 1 plugged into the first piece gives me a 2. Does 1 plugged into the second piece also give me a 2? Remember, you're squaring only the 1, so negative 3 plus 5, yes, that gives me a 2 also. We're good there. Go to the second equation. When you plug 1 into the first equation, you get negative 1 because there's nothing else to get. When you plug 1 into the second equation, do you also get negative 1? Yes. Yes. Check, you did it right. If you ever get different answers, something's wrong with your math, and you can go back and fix it. Do you have any questions? You guys did an awesome job today. Thank you very much.